Ever since I was in chemistry class, I heard that atoms are made up almost entirely of empty space. Thus, all matter is made up almost entirely of empty space, and so are we. And back when I was a kid, the old folks would say that somebody had a lot of empty space between their ears, but I think that was a saying left over from the 50s or 60s or something, because I haven't heard that in decades. At any rate, let's see how much empty space is in an atom. And this video will actually be a lesson on how to convert things to different sizes. So if you have something very small and you want to make it look very large, this is how you do it. This is similar to my star video where I calculated the space between stars. And in that video, I made the very large. I took the very large and shrunk it down to the very small. So here I'm taking the very small and I'm growing it up to the very large. Okay, so let's look at a helium atom right here. I was going to do hydrogen because I thought that would be the simplest. But hydrogen actually exists as a diatomic molecule, as H2, so there's two hydrogen atoms bonded together, and thus the numbers I got, I don't know if those were the numbers for a single hydrogen atom or if it was for the hydrogen molecule or what. So I went with helium because it just floats around by itself, so there's no confusion. So what I did here, I just Googled the radius of the atom, 3.1 times 10 to the negative 13th meters. And then the nucleus of the atom is 1.7 times 10 to the 15th. Let's just divide the big by the little. Take the size of the atom, divide it by the size of the nucleus, and we'll get a scalar quantity. Bit of trivia, that's scalar with an AR. If it's scalar with an ER, that's some sort of dental plaque scraping piece of equipment. So anyways, we got our atom right here, divided by the nucleus, gives us 182. I'm reshooting this video because there was a calculation error on my last video and I got like 8,000 or something. Don't know what happened there, but I try to double check the math, but I don't always. Okay, so atom divided by nucleus gives us this, 182. So the atom is 182 times larger than the nucleus. This doesn't matter if you use radius or diameter or circumference, you'll get the same ratio. Just don't use volume because that'll change your ratios, because a volume is like meter to the third power, and then you'll start getting some different ratios. Okay, so what this means is we can take the nucleus times our scalar, this number times the scalar, and get the size of our atom. And we can take the size of our atom here. So what I say here, nucleus times scalar gives the atom. You can take the atom, divide it by your scalar, and you'll get the size of the nucleus. So take this atom, make it whatever you want. Even though here we're dealing with like picometers or femtometers or something, you can make that atom like a centimeter or a meter or a mile if you want to. It doesn't matter. You can make that atom the size of a football field, divide it by your scalar, and then you'll have the size of your nucleus at that scale. I forgot to show my units right here, but the diameter of the atom divided by the diameter of the nucleus, those are both in meters. Meter divided by a meter is 1, so they cancel out, and you're left with a scalar quantity that actually has no units. And the reason that works out mathematically and logically is because you can take that scalar that has no units, multiply it by the nucleus that's in meters, and then you'll have the size of your atom right there, which is in meters, because then you'll have meters times something with no units, and that'll give you meters. If they both had meters, then you would end up with meters squared, and it would look like an area of something. So this is what it looks like. The atom is going to be atom over scalar equals the size of the nucleus. I'm just going to make it the size of about the size of a football field. 100 meters, 100 divided by 182 gives 0.5 meters or 50 centimeters. What this means is if you have an atom that has the same length or has the same diameter of a football field, right in the middle of that football field, you'll have a little 50 centimeter ball that'll represent the nucleus. I drew a scale model right here, 20 centimeters to represent the length of the football field. That'll be 200 millimeters. Divide that by our scalar quantity here so that we can have both the size of the atom and the size of the nucleus on the same scale. Comes out to be about a millimeter, which is that little dot right there. And we will be looking at a three-dimensional atom that's actually a sphere, even though this is just a two-dimensional rectangle. I tried to get the diameter of an electron, but I couldn't get any consistent results. Some sources said they were hundreds or 1,000 times smaller than the nucleus of an atom. Other sources said they had no diameter and they were just a point or just a wave. But I suppose if you use some of the sources that said an electron actually had a diameter that was hundreds or 1,000 times smaller than a nucleus, then on this football field scale right here, where the nucleus is a 50 centimeter ball right in the middle, then the electron would be like a gnat or a housefly or something buzzing around the perimeter. But then if it actually has no diameter, then you can't even do a size comparison. I wondered how this image right here translated to neutrinos passing through things, because when you look at this logically, you'd see how if a neutrino was really small and it would fly through things, the atoms, and not interact with anything. And neutrinos are famous for being able to go through like a light year of lead, and like half of the neutrinos will make it through and not interact with anything. Neutrinos pass through the entire Earth easily, and that's like 10 to the 50th number of atoms. But even at this scale right here, when you're dealing with a millimeter right there, compared to this, that's going to catch a lot of neutrinos. So when I looked into this, I just Googled it, and it said there's some sort of interaction between the neutrinos and the quarks inside the nucleus. And when you get down to that quantum scale there, things are weird because they're not quite particles and they're not quite waves. So basically even this picture right here doesn't explain how neutrinos can pass through so much material and not interact with anything. The larger atoms have more empty space in them compared to the smaller ones. I used helium here, which is a real small one. So next I'm going to look at one of the larger atoms to show that it has even more empty space in it. Let's look at plumbum, which is lead. Here's the atom, here's the nucleus. I double checked to make sure I did both of those in, I don't remember now if it was diameter or radius. I think it might have been diameter on both of those, but I made sure that they matched. So anyways, take your atom over your nucleus to get your scalar, and I get 26,000. So for helium, that ratio was less than 200, but for lead, it's 26,000. So the atom size is 26,000 times larger than the nucleus. Let's do a football field, which will be 100 meters, which is 100,000 millimeters. Divide that by our scalar, right there at 26,000, we get 3.8, so about 4 millimeters. So if a atom had the diameter of a football field, then its nucleus would have the diameter of about 4 millimeters. I think this is interesting because if you think about the size of a football field, if you had a little marble sitting somewhere near the middle of it that was only 4 millimeters in diameter, it'd be difficult to even find that little marble. So I thought that was kind of interesting. And this video also reminds me why I like to show all of my work, because occasionally there'll be a calculation error or a logic error, and then somebody can catch it.